Hi, thanks for joining me today. I'm going to share a fun number theory problem which was shortlisted for the 2020 IMO, so you know it's going to be a super interesting problem. We have a positive integer n which is at least 2, and we want to know, does there exist a collection of positive integers a1 up to an, which are not all the same, such that the arithmetic mean of any two of these ai's is always equal to the geometric mean of some subcollection of the ai's. So, in other words, you give me an n which is a positive integer which is at least 2, and we want to know, does there exist this kind of collection of positive integers? And note that I say collection and subcollection as opposed to set and subset to emphasise the fact that we are allowed repetitions. That's perfectly fine, but we can't have them all the same, because otherwise it's a bit too trivial. So you give me an n which is a positive integer at least 2. Does there exist a collection of positive integers a1 up to an? So I write them down, a1 up to an, such that whenever I take any two of these guys, compute their arithmetic mean. Let's call their arithmetic mean b, and it just so happens that b is the geometric mean of some subcollection of all the ai's. So we want to know, does such a collection of a1 up to an exist? Okay, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so I claim that the answer to this problem is no, i.e. in other words, if you give me an n bigger than or equal to 2, and you give me a collection of n positive integers which are not all the same, and we'll call these positive integers a1 up to an, well then I can always find two of these ai's, compute their arithmetic mean, and let's call that arithmetic mean, say, b for now, and b will have the property that whenever we take the geometric mean of any subcollection of the ai's, b will not be that geometric mean. Okay, but of course we've got to prove that, and the way we're going to prove it is sort of by contradiction. So we're going to suppose these ai's exist, and then we're going to result in a contradiction. Okay, so what we want to do is, firstly, I'm going to write down a result, or write down a kind of a claim, and it's without loss of generality, the greatest common divisor of these ai's, which we're supposing exist, is 1. Okay, so without loss of generality, their greatest common divisor is 1, and I'm going to leave that as an exercise to you to prove that this indeed is true. And essentially the argument is, well, if this wasn't 1, if this was, say, d, which is bigger than 1, well then you can divide each of these ai's by d and still kind of have a valid setup, because, you know, if you have an arithmetic mean equals a geometric mean, and then you divide every element by d, you're still going to have the arithmetic mean of all the new elements is equal to the geometric mean of all the new elements, because, you know, if you divide everything inside the geometric mean by d, and then take it out in the root, you're going to just have a d as a factor, and equally when you do the arithmetic mean, if you divide everything by d, you're just going to have a d as a factor as well. So those cancel. Okay, but if you're not convinced, just write down the algebra and convince yourself. But certainly we can assume without loss of generality that the greatest common divisors of these ai's is 1. So we're supposing these ai's exist. Then what we're going to do is let m be the index such that am is bigger than or equal to ai for all I equals 1 up to n. Okay, so am is simply the maximum of these guys here. The next thing we're going to do is notice that am certainly must be bigger than or equal to 2. Because remember, each of the ai's are positive integers, and so if am wasn't bigger than or equal to 2, because it's a positive integer it must be 1, but because it's the maximum of all these ai's, we then have all the ai's are 1. But that's not possible because we're assuming that all the ai's, or not all the ai's are the same, so there's at least 2 distinct. So certainly we must have am is bigger than or equal to 2, and that's quite nice because then it must have a prime factor. So let p be a prime dividing am, like so. The next thing we're going to do is introduce another one of these ai's. We're going to say let k be the index of this guy here, the maximum of the ai's for which p does not divide ai. So we look at each of these ai's here, and we only consider the ones where p does not divide the ai, and then we let k be the one that's big, the index of the one that's the biggest of this set here. So firstly, notice that this set here is certainly non-empty. Well, how do we know that? Well, if it was empty, then that would mean that p divides each of the ai's, but then that would contradict this guy here, because then the greatest common divisor of all the AIs would be at least p. Again, p is a prime, so it can't be equal to 1. Okay, so certainly this set is not empty, so this is well defined. And also what we want to notice is that AM is strictly bigger than AK. Well, it's certainly bigger than or equal to AK by this guy here, but notice that they can't be the same because P divides AM, but P does not divide AK because AK is in this set here. So certainly these two guys are distinct, and we have that AM is bigger than AK. And what I want to do is compute the arithmetic mean of these two guys. So the arithmetic mean of these two guys is simply going to be B, which is AM plus AK all over 2. And I claim that no matter which subcollection of the AIs we take and look at their geometric mean, that geometric mean can never be equal to B. But of course, I've got to prove that. Let me clean up the whiteboard and I'll continue. Okay, so we want to prove that B, which is just AM plus AK over 2, is never the geometric mean of any subcollection of the AIs. Well, suppose it was. So suppose it equals the tth root of, say, AI1 times AI2 times so on, all the way up to AIT. Okay, for some positive integer t. Okay, and we have this guy here equals this guy here. And what we're going to do is split this up into two different cases and show that each of those cases leads to a contradiction. So case 1, P does not divide any of these guys here. So it does not divide AI, let's say L, for L equals 1 up to T. So P does not divide any of these guys here. Well, then what do we know about each of these guys here? Well, certainly if we look at this set here, AI1 is going to be less than or equal to AK. Well, why is that? Because AI1, P does not divide it by this guy here, and P does not divide AI1, which means AI1 is in this set here, and AK is the maximum of this set, so AK is going to be bigger than or equal to AI1. Similarly, AK is going to be bigger than or equal to AI2, and so on all the way up to AIT. So we have this geometric mean here is going to be less than or equal to AK. So B is less than or equal to AK. But what do we know about AK? It's strictly less than AM from what we had before. The argument we had before, we had that AM is strictly bigger than AK. Well, what does that tell us? Then that means that AK must be strictly less than AM plus AK all over 2. Okay, so because essentially what I've done here is I've halved this equation here and then added a half AK to both sides. So that gives us AM plus AK over 2 is bigger than, if I add half AK to this, just gives me AK, which is exactly what I have here. But AM plus AK over 2 is simply equal to B. So we have that B is strictly less than B, which of course is a contradiction. So we must have that P divides at least one of these AIs, because otherwise we get that B is strictly less than B, and of course that is a contradiction. So now we want to consider the case where P divides at least one of these AIs and show that that also leads to a contradiction as well. But let me clean up the whiteboard first. Okay, so the second case you've got to consider is where P divides one of these guys here. So without loss of generality, we'll assume that P divides the first one. P divides AI1. The first thing I want to do is look at this equation here where we've got the geometric mean the arithmetic mean equals the geometric mean, and just multiply everything by 2. So I get a 2 here, I'm going to get rid of the 2 in the denominator here, and I'm going to put a 2 out here, like so. And now we're going to kind of split this into two further subcases, but I'm just going to talk through them. Firstly, we've got a product of positive integers within this root here, and we don't in general expect this to be a power of t. So when this guy here is not a power of t, so when I multiply all these AIs together, if I get a number which is not a power of t, well then when I take the tth root of it, it's going to be irrational. So certainly 2 times an irrational number would be irrational, so this right hand side as a whole would be irrational, and in particular not an integer. But on the left hand side we've got AM plus AK, which is clearly an integer, so we arrive at a contradiction. So we really only need to worry about when this guy here is a power of t. But then remember, we've got this extra piece of information here. So suppose this was a power of t. Let's call it z to the t. So z is a positive integer, and suppose it equals z to the t. Well, p divides AI1, so p is certainly going to divide the whole thing. But p divides a power of t, as p divides z to the t. And a very simple argument will tell you that this implies that p divides z. Okay? just by kind of properties of primes. So if p divides z, then that means that p to the t divides z to the t. So in fact, we can just put a t here. So we have that p to the t divides this number here. So let's quickly go over that. We have this number here, we're supposing is a power of t, because we've just dealt with the case where it's not a power of t. So we're supposing this is a power of t, and we know that p divides it. But because it's a power of t and p is a prime which divides it, we must have that p to the t divides this guy here. So p to the t divides this guy here. So when I take the tth root, I'm certainly going to get a multiple of p. So all in all, this is just going to equal c times p, where c here is just some positive integer. It's just going to be a multiple of p. So am plus ak is going to be equal to a multiple of p. But this is actually a contradiction, and to see why, let's just look at both sides mod p. So if we look at both sides mods p, obviously the right hand side is going to be 0, because it's very clearly a multiple of p. Am is a multiple of p by this guy here, so that's going to be 0, so I'm going to be left with ak is congruent to 0 mod p, or in other words, p divides ak. But if we have a look up at this line here, we've insisted that ak is a maximum of this set here, so in particular ak is in this set, so that means that p does not divide ak, but that of course contradicts what we've written down here, and we've arrived at a contradiction, and that of course solves our problem. So we had to split it into two different cases, but both of those led to contradictions, which means that the statement of the solution to our problem is no. So in other words, if you give me an n bigger than or equal to 2, and you give me a collection of n positive integers, a1 up to an, then it cannot have the property that, or in other words, there will always exist two AIs, such that when I take their arithmetic mean, it will not equal the geometric mean of any of the other guys. Anyway, that's all for this video. I hope you have enjoyed it. Thank you for watching. I'll catch you in the next one. Have a great day.